series that looks noisy, and again, remember this issue of finding the signal and what is noise might not be noise, but suppose you have some time series. This is, again, the intensity of some laser, changing some control parameter. When you use a threshold, when you try to filter out results, you might find very different results. So that's another thing that you might think of. Not only the different methods can give you different results, but also the way you process the data can be very important and can change a lot of what you obtain. And it's not that it's wrong, it's complementary information. What you might see when you look at the whole time series might be different to what you obtain if you just look, for instance, at extreme values. Okay, so if you look at autocorrelation, the autocorrelation is the same idea as the cross-correlation that some people mentioned yesterday, only that it's a time series with itself. Okay, a time series with itself, this is here. So I compare the value of a variable with the variable at a certain past. And this is without the mean and normalized to the standard deviation. This is the autocorrelation function. I'm introducing this now because I'm going to use it to compute cross-correlation. The only difference is that instead of using the same time series with a lag, in the cross-correlation case, you consider two time series, different, okay? But the formula is the same. You compare with a certain lag. So with respect to the data that I showed you before, I told you there are different parameters, and we change the parameters, and we can see that the cross-correlation is very high if you use a small lag, if you're comparing nearby values in the time series. But if you increase this lag, the correlation is small, okay? And there is this periodicity. This type of periodicity you can find also if you analyze, for instance, the caudal, the water in a river, okay? The water in the river today is highly correlated tomorrow and day after tomorrow. But then there is the decrease of the correlation. This decreases relatively fast, but then it recovers because there is a seasonality. In 1 year time, you probably have similar amount of water in the river and so on. So basically, this is what you can see with this cross-correlation, which is easily changed to, this is the autocorrelation. You can change to cross-correlation just by using different variables in these different variables here and here. Now, you can do better than this, and you can calculate the entropy. And I didn't mention that before because I wanted Osvaldo to introduce the concept of entropy. The entropy is kind of an autocorrelation measure, only that is nonlinear. So you can calculate the entropy for the same data, and you see that for some parameter, not always, the entropy detects something different. Okay, this entropy is calculated from the time series with ordinal patterns, but instead of comparing consecutive values, we use a lag. It's the same as redefining the sampling time, okay? So we compute the entropy, the permutation entropy that Osvaldo introduced yesterday, change this lag, and here you see that the periodicity is clearly not linear, right? So again, this message here is correlation is a linear measure, autocorrelation or cross-correlation. Entropy gives nonlinear, detects nonlinearities. And the equivalent in bivariate analysis, that is what we're going to study now, is the mutual information. The mutual information, when you use the mutual information, you might not find exactly the same results as when you use cross-correlation. Cross-correlation is linear, and measures that are defined in terms of information theory that depend on some probabilities that you calculate using different techniques, for instance, ordinal patterns, can be very different. Okay, so now I do go to bivariate analysis, which basically means comparing two time series. And I go back to the example of my first class of stochastic resonance. So how a bistable system encodes a very small signal. And I show you this time series, and I show you this. So changing the level of noise my input signal is encoded in different ways. So now I'm going to use the cross correlation, which is this expression here. Now I have two different time series. I have a lag here, and the time series I have normalized already to zero mean and unit variance. So that's why I don't subtract the mean value. So this is the cross correlation. As I said, it's a linear measure, but it allows me to see where is maximum this correlation, for which noise level I will have a resonance. I can encode this input signal in the output in the best way. So this is the noise level, and here we have the cross correlation computed with zero lag. So this is the input, which would be this. This here is the output, which would be one of these time series. And comparing these two at zero lag, I see that there is a resonance for a certain level of noise. So this is the idea of bivariate analysis. I compare two time series and try to find where they are correlated. But keep in mind that the correlation that you will detect with this type of function is a linear correlation. What does it mean? It means if you plot one versus the other, and you can use a lag if you want here, well, if the points, if you get a cloud of points, right? If your cloud of points is like this, you will have a high correlation equal to 1. If it's over here, it might be negative correlation. And all these values gives you the degree of correlation. For instance, if you have a cloud of points with no structure whatsoever, then you will have a 0. If it's perfectly correlated, you will always have a 1 or a -1, but you don't have information about the slope. It's 1 or -1, but you don't know. All these are the same. The main problem here is that down here you see that these two variables are not independent. Just by visual inspection, it's clear that they are not independent. The only independent case is up here. But if you compute the cross correlation, you will get a 0, which is misleading because you will think it's no correlation between X and Y. That's not true. So another important thing, correlation is not causality. People have mentioned this before. I'm going to go fast here, but I'm showing you two time series, the number of senators in the US Senate in some period of time, several 26 years, and the number of sunspots, the spots in the sun. Clearly, there shouldn't be any correlations between these magnitudes. However, if you calculate this correlation, it gives you a 0.52. And a lot of people says, oh, if the correlation is above 0.5, then it's significant. And if it's below 0.5, it's not significant. But clearly, it's an example here of an insignificant correlation, which is above 0.5. So this example here is just for you to remember that you always need to perform a proper significant test, okay? This has to be done carefully, and if you do this carefully, and I will give you a reference in a while, then really you will see that this value is not significant. It doesn't matter whether it is above 0.5, proper surrogate testing will let you know that this is not significant. It's really funny to look at this webpage, spurious correlations, because you will find correlations about anything, really. It's quite interesting. So obviously correlation is not causality, but sometimes there are some examples, like here, the number of people voting for Biden and the number of people that had received the first COVID vaccination. So you will see that the people that didn't vote for Biden did not really receive the vaccine. Obviously, there is no causality here, right? Causality is not correlation, but there are things that you can think of, no? That you need to think of. Okay, so nonlinear measures of correlations, the equivalent of entropy for univariate analysis, is mutual information for bivariate analysis. It's computed from probabilities. You can extract probabilities in different ways, ordinal patterns, symbols. Osvaldo mentioned the horizontal visibility graph. There are many ways to compute probabilities from a time series. And then the mutual information is the probability or extracted from one time series, from the other, and then the showing probability that a symbol occurs in X and another symbol occurs in Y. So this magnitude is obviously symmetric. The same happens with the cross correlation. And if the time series are independent, then the showing probability is a product. Because you have this product here, and this have the product, it is in the denominator, you have logarithm of 1, which is equal to 0, right? So the mutual information is 0 if you have independent time series. Now, in fact, this is not always true, because this equality is a mathematical expression, but in real data, with limited data, this will always be a positive number, okay? It cannot be any way. So you really, again, need to be very careful with the surrogate analysis, and you really need to test what does your value actually mean. It can be computed with a lag, so you can look at what happens in one time series now and the other time series in some other time. And you can also calculate this with probabilities. If the two processes are stochastic Gaussian processes, the mutual information is directly related with the correlation. So there's a formula here, and there's no point in calculating both. Other thing you can do, and again I said, when you use a threshold, you define events, and you can just analyze those events, is to try to find simultaneous or synchronized events that might not be simultaneous, but might be related in the two time series. For example, consider two EEG signals and see these are separated, and see that there is an event here that is probably correlated. So this event synchronization means that you have to define somehow events and then count the number of times an event occurs in X. Shortly after, within some interval of time, an event occurs in Y. And then do the same on the other direction. So basically, you can calculate two magnitudes. One, which says normalize it in this way. This gives you values between 0 and 1, and -1 and 1. So basically, if this is 1, it means that the events are fully synchronized. It means that whenever there's an event in one time series, there'll be an event in the other time series. The other magnitude tells you who is lagging and who is ahead. If this is 1, then the events in X always occur before in Y. It could be -1, and it would be the opposite case. So when one magnitude, you find synchronized events, and with the other magnitude, you see who is lagging, or if this Q is 0, means sometimes X is ahead, sometimes Y is ahead, okay? So this is a way to, again, define events and just analyze how synchronized these events are. Okay, and there are many other methods to compare, no? If you are interested, you can look at this paper in which they compare actually 6 methods: phase synchronization, cross-correlation, mutual information, event synchronization, coherence, and some other. And the conclusion is basically linear and nonlinear measures applied to EEG signals. And besides the mutual information, which was not robust due to low number of data points, it's true that when you have to calculate probabilities that depend on two variables, you need to have a lot of data. Remember, you need, for each bin in a probability distribution, you need to have, on average, 10 data points. So if you calculate a distribution of values in a 2D space with 10 bins and 10 bins, you need at least 100 data points as a minimum. So the mutual information requires a lot of data. But all the others gave similar tendency to the synchronization levels. So in this case, in this particular case, there's no particularly good measure or preferred measure. But there is a very detailed study, and you can look if you are interested for other measures of detecting synchronization. The other thing is causality, of course. This is the typical, the most popular method is Granger causality. I just explained the philosophy. It's a linear method. And it can be applied whenever these two processes, 1 and 2, are considered autoregressive processes. This means that process 1 can be described linear superposition of the past of process 1, plus some residual variability. And process 1 can also be described in the same way, but we can consider adding the past of process 2. Maybe this is a better description. Maybe the residual error is less. If this is the case, then we can say that the process 2 improves the description of process 1, right? So we can say that process 2 is causally related to process 1, because taking into account the information of process 2 improves my forecast of process 1. This is Grancher causality. This has been applied to all fields of science and technology, and is basically a linear approach. All these, you can see, are adding past terms, but it's a linear way, right? So it's very useful. You need to try this if you are looking for causal interactions, but keep in mind that it's linear. So the other way is the transfer entropy, which is the equivalent of the entropy for univariate analysis. For bivariate analysis, this is a conditional mutual information. It's the mutual information that I defined before, but taking into account given the past of one of the variables. So it's a mutual information of x and y considering given the past of x. So this is not symmetric anymore. These two magnitudes are not the same, and one can define a directionality index basically in the difference between these two. And it's demonstrated too that if we are dealing with Gaussian processes, then the transfer entropy is equivalent, gives exactly the same results as the Grancher causality, if the processes are Gaussian, stochastic Gaussian process. If they are not, then this transfer entropy can give very different results. And also can be computed from probabilities of symbols, because it's a mutual information that can also be computed using ordinal probabilities or any other type of probabilities. If you want to read more about it, this report here has different methods to detect causality. What are main problems with all these methods? Basically, we cannot, if we have a chain, we might detect a link between X and zeta. So this might be, of course, there is transfer of information, but it's not direct transfer. And then we might have a situation like this when we have a process X that affects two variables, and we will, because of this common driver, detect some link here, which might be fake. Just to put an example, this type, whatever you can find, depends on the method you use, likely. And you have a classical example in this field is how the sea surface temperature affects the population of anchovy and sardine. No? The anchovy eats the sardine, and both are affected by the temperature, or these two are totally indirected, unrelated, and they're just affected by the temperature. So different methods would give you different information. And also you need to take into account that the transfer entropy has the same problem as the mutual information. It demands computationally, and data also requires a lot of data, because you have to have probabilities, conditional probabilities, and with two variables, and that it requires a lot of data. A simple solution is to use, for the transfer entropy, the expression that is only valid for Gaussian processes. We know this is only valid for Gaussian, but we use it anyway. If it's not Gaussian, it's not Gaussian. Okay, does it work? Sometimes it works, sometimes it doesn't work. And if you want to test this method, here I give the references and the code is available. So it makes things much faster, but we know for sure that sometimes it doesn't work. Now in this paper, we also show that the transfer entropy doesn't work. So when this fails, also transfer entropy fails. Okay, so there are many methods that have been proposed over the years, and you can find a comparison of 6 methods of the detection of causality in bivariate time series analysis. You can find results here. I also want to mention that what the results that you obtain also depend on the sampling of the data. In the paper that I cited, that we did with my student Ricardo, he analyzed El Niño and an Indian monsoon. And in a short time scale, when you look at data that is sampled monthly, El monsoon affects El Niño. But when you look at data that is yearly sample, and El Niño is a yearly phenomenon, then you have the opposite direction of causality. So it not only depends on the method, but also depends on the data and the resolution of the data that you are analyzing. Okay, and now I'm moving to the situation in which we're going to analyze all together several time series. And basically, I'm going to start talking about the simplest approach to this, which is to construct a network using bivariate correlation or causality. So compare pairs of time series. I think we already present, not exactly this example, but the idea of functional networks was presented by, I don't know, maybe Jesus. So you build a correlation matrix, taking pairs of time series, for instance, recorded in the brain. Compare pair to pair, okay? So you have your correlation matrix. The color here represents the value from 1 to -1. And you have to use some significance to see what is significant and what it is not significant. The 0.52 that I showed you before is not significant. So you filter out. That's the process that is called thresholding. And you end up with zeros and ones, and then you represent this as a network. So this is a simpler way to take a group of time series, do pairwise comparisons, select only significant values, and build your network. And here is done by correlation, but you can use any of the previous methods that I explained before. So mutual information, transfer entropy, Granger causality, whatever. If you use symmetric methods, you will end up with a symmetric matrix. And if you use methods that take into account directionality, you will have a matrix with some links, directed links. So basically, this is the method, the idea of thresholding. You have some similarity value. This can be anything, cross-correlation, mutual information, transfer entropy, whatever. If this value is larger than a threshold, these 2 time series are connected, otherwise they're not. And then what do we do with this graph? What do we do? Typically, this is something that, yes, Jesus explained it, you characterize with a degree distribution. So if you end up with something like this, which is regular, the degree distribution is a delta, because all the nodes have the same number of links, right? This is either 2 or n, but it's all the same. This is not a practical situation. If you end up with a random, as Jesus said, you end up with some Gaussian form for the degree distribution or a power law, right? Okay, so these are ways to characterize a large set of time series. The time series you transform into a network and then characterize the network. How to compare these distributions? We want to know if 2 networks are similar or not. So here Osvaldo yesterday introduced distances between distributions. You extract a distribution from the network, for instance, the degree distribution, and then you have another network, for instance, consider brain signals between different subjects. From one subject, you obtain a network. From the other subject, you obtain another network, and you want to see if these are, if one is alcoholic and the other no, for instance, or has some disease or whatever. So you can compare using the simplest way, which is Euclidean, but this has the problem that the two distributions have to be over the same grid of points, right? Because we are comparing value by value. That's a problem. The other ways that Osvaldo mentioned were extract probabilities and compare these probabilities, for instance, in this case, using an information measure. And this is not symmetric, so it's not a proper distance, but the Hansen divergence is a symmetric measure, and it allows to compare two distributions without having the two distributions having to have the same number of bins to compare bin by bin, okay? So you extract, for instance, the entropy here, I have it. This entropy assumes the entropy of a probability, the entropy of another probability, and the difference. But to make it symmetric, you compute it in this way. Okay, I give you also this reference because here there are like 30 or something measures to compare probabilities. Okay, there are many, many, many different ways to compare two probabilities. And again, that's the measure you use will affect your results. Now, again, is this good enough? Depends. It depends. How different are two graphs? We can use this Hamming distance, which is a simplest way of comparing networks without using distributions, comparing directly the values. No, if there is a link, if there's a link in one network and there is no link in the other one, we add here. So we are adding all the difference. All the missing links, we put them in this and we count. Okay? Is this good enough? I don't know. First, it has the problem that the networks have to be exactly the same size, right? If you end up with brain or networks that have different size, it's better to extract a distribution, extract another distribution, and compare the distributions. But also has a problem. Imagine that they are the same size, the networks. And imagine you want to compare these ones. Okay, the difference is just one link. Here, this link is missing here, and here, this link is missing here. Now, the distance, if you use something like this, will be the same, because it's just one. But we can see clearly that this missing link is crucial, while this missing link only leaves a small node here isolated, okay? So again, depending on the level of precision, you might have to use some more advanced methods to compare networks, okay? And there are many, and I'm just putting here an example of a method to quantify differences when you have this type of situation in which all the nodes are unlabeled and you have networks that are and do not have direction. But there are many ways, and there are many articles that discuss which is an efficient way to detect important but small differences in networks. Okay, so what I'm going to talk about is a little bit different. So let's see if we can try to infer the structure of the system from my observations. No? This is a problem that is called network reconstruction, network inference, and basically the idea is how to select this threshold to have perfect reconstruction of reality. So I'm observing the signals of a system, and I don't know how the system is really connected. I choose a threshold, and then I decide these two nodes are connected. But how can we see if this is a good approach or not? And important, how can we keep links that are in principle small, but are significant? I mean, for instance, in networks that are embedded in a space, and also Jesus talked about this yesterday, if I keep only the most strong links, I will keep the trivial links, because it's obvious that people that are really nearby will be strongly correlated. We know this. We don't need to do all this study for this. We want to detect links that are not trivial, that might be from far away areas. right? And it means that if I choose a threshold that is very significant, I will cut all this information, right? So this is eventually a classification problem, no? If the interaction exists or does not exist. And then I need to see what type of errors do I make when I decide this link exists, this link does not exist. There are two types of errors represented by this example, which is type 1. The link exists, eyesight exists, you're pregnant, but you're not pregnant, clearly. And there's another possibility that I say you're not pregnant, but obviously you're pregnant, okay? So these type of errors are called false positives, the false positives, and the false negatives, or type 1 and type 2 errors, okay? And I'm having my technique or method to decide who is there, which exists and which doesn't exist, and I have to somehow quantify how this method works, the performance of the criterion I selected to classify. This is a classification problem, and I'm going to talk later about this in relationship to machine learning, but you need to have some performance measure. You use a criterion to classify, and then you have to somehow estimate how this criterion works. So the accuracy is how often the classifier is correct. The misclassification is the error rate, how often it's wrong. And then you have the true positives, as we said, which is also called recall. When it's yes, how often I detect the yes. The false positive rate is when it's no, how often do I predict yes, I make a mistake. And the specificity is when it's no, how often I actually predict not, and the precision, etc. There are other, I didn't list all of them. These are ways to quantify how good the criterion I'm using to classify existing, non-existing links works. So basically, what I'm going to talk about is the receiver operating characteristic curve. Who knows about this? Okay, a few of you are familiar with this. Excellent. Excellent. Okay, so basically you plot one versus the other. You change your threshold, right? And let's consider you use one similarity measure. If you choose a very weak threshold, a very flexible threshold, everything is a link. If everything is a link, for sure I'm detecting all the links that exist, but I'm making lots of mistakes. I detect also all the possible links. So my false positive rate is maximum, right? Now, if I'm gradually increasing my threshold, I move in a way that I start to lose the real links, and I also lose the links that do not exist. Ideally, if my method is perfect, I would move along the vertical line here. I will keep all my positives, and I will eliminate the links that do not exist. My ideal position is to find a threshold that gives me this point here. This is perfect reconstruction. I identify all the links, and I don't make any mistake. I have 0 false positives, right? And then if I continue increasing my threshold, then I move, I end up, if I put a threshold too high, then I don't detect anything, right? I don't detect anything that is, I don't have any mistake, but I don't detect any positive either, right? So somehow this area, the area under this curve, is what matters. The different methods that I use, the different similarity quantifiers, give different performance in terms of the ROC curve. And the area under the ROC curve is what is used to see how good or how bad a measure is. What we are analyzing is a similarity measure. And the best optimal threshold is the one that takes me closest to this point. So the best method to classify is the similarity measure that takes, you can see these 3 cases is more or less the same. Now, if I do this randomly, just throwing a coin, right? Yes, no, in totally arbitrary way, I move the diagonal. If you have enough data, then you are rejecting links with no criterion whatsoever, and eventually you reject all of them. So basically, this putting a threshold, you have two distributions, those that exist, those that do not exist. And if you put the threshold here, everything here is a true negative, the blue. But I'm also missing some of the reds. These ones are false negatives. I put them on this side of my threshold. I'm saying they don't exist, but they actually belong to the distribution of things that, of links that exist. So this is my false negatives. Now, if I put my threshold here, I would consider that all of these are above the threshold and therefore exist. And I'm making a huge amount of errors here. All these are false positive because belong to the distributions. Okay? So ideal is easy. You can get perfect reconstruction or perfect classification if these two distributions are well separated. The links that do not exist, the cross correlations are very small, and the links that exist have high, strong correlations. But that's typically not reality. In real situations, I'm interested about the weak. I'm actually interested here sometimes. I want to detect links that exist but are weak, might be below my significant threshold. A link in a climate network between time series in Japan and a time series in Australia, the cross correlation might be very small, but there might be some relationships, physical relationships, some physical processes that make correlations. So that's a challenge. Now, if you have unbalanced data, which means think of a population of people and only a few have cancer, those are the ones you want to detect. It's not half the population that have cancer. If the set is unbalanced, instead of using the ROC curve, you use the precision recall, which is the precision versus the recall, and those were indicated in the previous table, okay? And this is because they don't depend on how many negative cases are. If you have a large population of a lot of people and only 2 or 3 cancer, or if you are detecting a problem known as outliers, outliers by definition are very few anomalies in your data, then it's better to use this curve, precision recall, instead of ROC. Anyway, so we did a study thinking, how can we reconstruct a network? So let's say, suppose we know the structure of the network. We know how the systems are connected. Okay, I have 15 minutes. We know how they are connected. We construct the electronic circuit or whatever. We know the exact connectivity, but we pretend we don't know. And then we compare different methods. Of course, the results will depend on the toy model that I use. This is just an exercise, let's say. Let's consider the Kuramoto, because people have been talking about the Kuramoto. We can talk about the Kuramoto too. So we do our simulations. We know how this connectivity matrix is. It's a random matrix. We consider only 12 Kuramotos. We can simulate the time series with noise. And then we analyze the data. And then we use our similarity measures and see if we can reconstruct this matrix, okay? All right, so we can look at the phases, and we can use different methods to compare. Cross-correlation, the mutual information, or the mutual information computed with ordinal patterns. Just looking at the phases. And of course, the results depend on the coupling. Essentially, if the coupling is very weak, it'll be very difficult to detect the links. The stronger the coupling is, the stronger the links are, the links that exist will be, in principle, easier to detect. And in fact, we see that the cross-correlation works quite well, and after certain coupling, I can detect all. The true positive rate is equal to 1. Now, I make mistakes here, because the false positive rate doesn't go to 0. I keep detecting as existing links that actually do not exist. And this is the best measure. The other measures are not so good. The symbolic method works really bad. So again, keep in mind that results strongly will depend that you use the right approach to compare the data. Okay, but the phases are not really physical magnitudes, right? Because physical magnitudes do not depend on the phases, depend on some observable of the phase or the frequency. So let's look at the observable, some function of the phase, right? Let's say the sign of the phase. That's what can appear in physical variables. If we look at an observable, like the sine or cosine or some function of the phase, periodic function, of course, you can see that the reconstruction is not good, okay? And here you have the reference, and of course the reconstruction depends on the threshold that you choose, and we change the threshold, and I'm showing you the best results we were able to obtain. For each coupling, we had to select the best threshold, and we made various error bars mean different initial conditions, different noise, and so on. Now, what if I could look at the frequencies? The frequencies, of course, are the derivative of the phase, and the Kuramotos are coupled through the frequencies. And here we have the good news. It's possible. For the cross-correlation, eventually, with sufficient coupling, I get all the true positives, and I get 0 false positives. Perfect reconstruction is possible when looking at the frequencies, when using cross-correlation. However, we only have 12 oscillators. It's a small network. It's not directed, and there were not that many links to detect. So and we had a lot of data. So now we went, okay, let's do experiments. And we consider electronic circuits, of which Jesus also talked in his talk. We consider 12 electronic circuits, and here we measure a physical variable, which is the voltage, right? If we want to compare with the Kuramoto situation, you can see that the voltage has oscillations, and we need to recover a phase. Many ways to extract a phase from a time series. I didn't have time to talk about this, but a well-known method is the Hilbert transform. You apply the Hilbert transform, and you obtain some phase. And from the phase, we can calculate the observable and so on. So for the Kuramoto oscillators, we knew the phase that comes from the equations. We calculate the derivative and calculate the frequencies and observable. From the Rosler oscillators, we have the phase computed. So we measure the voltage. From the voltage, we measure the phase with the Hilbert transform, and then the derivative. But again, we have 3 methods: cross-correlation, mutual information, ordinal patterns, and we have 3 variables to analyze: the phase, the frequency, and the observable, which in this case is really what we do observe with the experiment. So which do you expect will work better? Which combination? Cross-correlation? Okay. No, don't worry. I'll give you the answer because I want to go fast to my last part of the talk. Doesn't matter. Essentially, the result is, it doesn't matter if you calculate from the observable, from the phases, from the frequencies, which measure you use. You can see that in the experimental data. That is peace of mind. It's not, your results will, at least in this case, will not depend so much on you choosing the right method and the right variable. But again, this is a toy model. It's just an example for you to think of, and different data might be different. Maybe you will have an optimal method and an optimal variable to recover the network. I don't know. Okay, so and I'm going to finish with some example of machine learning. I want to finish with this image analysis of retina images. Essentially, the message is many of the techniques that I have been explaining, that we're talking about for time series, can be adapted for images and can also be adapted for videos, okay? So basically, we are interested on this because it allows for the diagnosis of eye diseases. It's also biometric identification. You look and the door of the car can open or your mobile can unlock. And it's also an opportunity, a window to the brain. You can detect a lot of problems, neurological problems, by inspecting vision okay? And we had a project a while ago, a European project, working on biomedical signals. So let me first give a quick, very brief introduction to machine learning for people that are not familiar at all with what this is. It's a computer program that learns from experience with respect to some task and performance measure P. So we have the task, the experience, and how to measure, no? And the performance at this task, measured by this performance measure, will improve with experience. Okay, what does this mean? Let me give you an example. Suppose you have your email program that wants to classify your emails as spam, whether they are or not spam. So the task is classify emails spam or not spam. The experience is you do this, so the program learns from what you do. You give what is called labeled data, no? And then in the future, will, without your intervention, put an email in the spam box, okay? And the performance is the fraction of emails that were correctly classified. So if you go to the spam box and recover an email that was not spam, then this will decrease the performance. Now, there are many times, I'm just going to talk about supervised learning and unsupervised learning. In one case, we have to give a labeled training set, like say which email is spam, which one is not. And there are two things, to classify or regression to predict what to do with a new data point. The other possibility is unsupervised. There's no labels, and that basically is the clustering method. Now, the clustering method basically divides a population in two classes with some line here. And here, network techniques can be very useful because if you construct a network from here, then there are algorithms to detect communities. And then this element that was wrongly classified can be identified as belonging to the right community, okay? However, you have to be aware of the problem of overfitting. And this is just a representation of what it means. If you have enough parameters, you can tune your system to have perfect classification, okay? And perfectly separate. But if you get a new element, this system will not perform as good as this one. So usually, optimal performance does not give you a robust performance. If you want to have a system that is robust, you need to be tolerant to a smaller amount of errors. If you want to optimize your system with your training data to do not make any mistake, it's probable that when it sees new data, it won't be as reliable as one method, one system that is not so optimized. Okay, so this is the idea of classification, finding a line here that separates two groups. And regression is more like trying to find some equation that describes these points. And in particular, more in general, you will have some sort of input, some system that does something, and an output, and you want to predict or find relationships between input and output. Now, typically, supervised algorithms are classified in two types. I'm not going to go into neural networks because this has been explained before by Jordi. So it's just elements with nonlinear activation functions. And the decision tree is what to do in different situations until you get up to a certain number of classification between different possibilities. And k-nearest neighbors consist of having two groups. And then if I have a new that comes from instance from a labeled set, have a new element to classify or to predict, this one is good for both, and I'll explain in a minute, you need to look at the nearest neighbors and which group it will belong. To forecast, the idea is that we have a time series and we want to forecast the next value, okay? So basically this is what I know, and I want to forecast the value that comes after this one. And this will be some sort of function of my data, right? That's what I'm trying to do, try to learn this function. How do I evaluate the performance? As we said, there are many ways, cross-correlation, many magnitudes, but I can, assuming that I know, I can compare my forecast with the real value and do this average on time and calculate the mean absolute relative error, but there are other ways, okay? And one way to forecast is by k-means, nearest neighbors. So in my training set, I put my point, and I look the neighbors, and then evaluate the next one, given the position of the neighbors. The other possibility is to use what is called the inner product, to consider that this function is a sort of parabola, let's say, of the information I know. So these coefficients can be obtained by optimization techniques, and then this can be linear or non-linear using some expression for these products. If you want to read more about this, you can take a look at these machine learning algorithms for predicting chaotic pulses. It's very comparing different techniques, machine learning techniques, to compare the amplitude of the next pulse. Okay, so I go back to the eyes images, the fundus. We had 45 high-resolution images. Oh, I'm running late. Very high-resolution images. We have 15 patients with healthy, glaucoma, and diabetes. And basically, we had two things. We had the image, and we have what is called a manual segmentation, which looks very good. That was done by a doctor, that medical doctor, that pixel by pixel indicated whether this pixel is part of a network or not, or there's nothing there. And we want to design an algorithm that unsupervisedly segments the image. First of all, because it's not practical to have one person inspecting, imagine all these pixels and a lot of data, impossible. This has to be done automatically. Then extract a network from the image and then characterize that network, okay? So what I wanted to say is that we adapted a method for cultural neural networks that was used in Shorty's lab. So Shorty's lab has this two-dimensional network. He takes pictures and he extracts the network. This can be adapted to analyze this type of image. It was a lot of work done by a PhD student, Pablo, and Irene in Madrid, but this can be done, and we can obtain what is called an unsupervised way, this segmentation. I compare to you with the manual one. You can see, of course, the manual is much better, but it's not practical. Okay, so we wanted this was an important step for us to do this in unsupervised way. And yeah, the next step was to identify the optical nerve and all the nodes, and then to characterize this network. I'm not going to go into distance to this because we are using distances between networks. So we have different patients, we have different networks, and we go to this problem that I told you before, how to compare these networks. The networks that we obtain are different, have different number of nodes, different number of links, and the way to compare them has to be done in a good way. If we have the manual segmentation, a lot of measures work, the weights, the distribution of distances, they work, but that's not what we want. We want this to work in the automatic one. And in the automatic segmentation, the fractal dimension and the mean distribution can separate two or three groups, healthy, diabetic, and retinopathology. And if you look at simple measures, like the number of nodes we obtain or the number of links, that doesn't separate at all. Okay, so to conclude, I have shown you that bivariate and multivariate methods can allow uncover relationship in data, that different similarity measures are available for inferring the connectivity, that different methods can uncover different properties, and that methods can be adapted to analyze different type of data. You can analyze a network from a time series or from an image or from cultural neurons to extract, to analyze the eye, okay? So I want to finish thanking my PhD students. Over the years, I have been presenting you work by Andres, that studied the laser, by Pepe, that studied the neurons, by Jordi, that did also experiments comparing forced lasers and neurons, Maria, that studied neuronal coding, all these probabilities that I show you, Carlos, that did this work on differentiating brain states that we later continue with Bruno, Giulio Tirabassi did the inferring the connectivity of the Kuramoto oscillators, the chaotic circuits, and he also used the entropy for vegetation, for detecting transitions in vegetation fields. This is Pablo here that did this network analysis of retina fundus and also the machine learning algorithms. And finally, the last student last year, he graduated and he was working on pseudo-transfer entropy for causal detection. And that's all. Thank you for your attention.
Thank you, Cristina. Questions? Oh, okay.
Maybe I have many, I'll ask some later, but when you were showing the study where you tested the different types of methods on Kuramoto models and stuff like that, what was the mutual information that was not ordinary pattern mutual information?
The two, the mutual information normal and the mutual information ordinal patterns didn't work.
Yeah, but the question is, how did you extract the probability distribution for that mutual information?
By comparing, I think, 4 values. I'm not exactly sure, 3 or 4 values. You compute probabilities, and then you calculate the probability of one pattern in one time series and another pattern in another time series.
Okay.
A bivariate probability distribution, a joint probability distribution.
Okay.
I would like to know if you ever tried to do an ensemble of symmetric metrics to create functional graphs.
If we can do ensemble.
Yeah, for example, if you want to reconstruct the Kuramoto model graph, you could try to do an ensemble of cross-correlation from multiple information. I know that's complicated in an interpretable sense,
yes,
but could lead to good results.
Yes.
So,
absolutely, it could be done. I think you're meaning that consider at a given time, consider that as information, like an image, no? Take a photo of the network, analyze this, and then change time and analyze this, no? Maybe? I'm not sure if I understand, but yes, I think I captured the idea. What we have considered is one time series, another time series, and cross-correlate this. Yeah. But we could use a spatial version of ordinal patterns, for instance, and to analyze the situation of the network at a given time. No? At a given time, and see what happens at that time. That would be a good idea if you have temporally evolving networks, which is actually a main problem for instance, epidemiology, because they analyze a network considering the static situation. But normally your relationship change in time, and your links blink, no? So yes, it would be, we had a static network too. The coefficients were constant in time. But if the coefficients change in time, then we definitely need a different approach. We have to reconstruct the network at each time. I don't know if that was in the direction, yeah, more or less. Okay.
Okay, I'm going to ask you a couple of questions. One is about the machine learning algorithms for predicting the amplitude of chaotic laser pulses. My question is, once you use, let's say, a given pulse to do the machine learning with it and predict what will be the other one. Okay, you generate a new pulse with the machine learning algorithm. I mean, is the attractor the same?
We didn't reconstruct the attractor. We only wanted to reconstruct the amplitude of the next pulse. Okay? So that is a different problem. So here, the sequence is a sequence of pulses.
Yeah.
The amplitude of the pulses.
Yeah,
okay?
but if you record all the pulses that you have predicted and you plot the attractor, is it the same as the attractor
real
of the
attractor.
original?
I don't know, but you can measure this with this. This is the usual way of machine learning measure the performance.
Okay. No,
how
but
good your forecast is.
Yeah, okay.
Yes, but here we did compare many different methods because there's a plural here. Actually, the novelty of this work was comparing different ways to forecast something. Okay.
Okay. Yeah. Who else has a question? Yeah.
I was just going to make some comments for your question. There are some regression algorithms that can reconstruct the attractor. So you can recover the equations of this attractor based on data.
Yeah.
And then you can apply those measures and compare to what you have from data. So
Absolutely.
there are those techniques too. So
yeah.
Okay, thank you. And I have another question. I don't know. I mean about this this research on the eye and the different illnesses. I mean, have you checked on maculopathy?
The macula.
Maculopathy, yeah, the macular degeneration.
We didn't have data for that. In fact, we had very little data.
Yeah.
We had only 15 patients for each category. The problem is that this method detects very small difference in the network. So that means you need high-resolution data, and that's not available. There are large databases of fundus images.
Yeah.
If somebody wants to take the challenge, be my guest. But the resolution is not sufficiently high to really be able to detect these small differences in the network, which determines whether you have macular degeneration or you have what we want to do, of course, is to detect early warning signals of diabetics,
that would be great.
right?
Yeah.
Exacto. So for that, you really need high-resolution data, and it's very difficult. It's very difficult.
Okay. Well, any other question? Okay, well, I'm sorry.
So if you want to predict, you want to detect like the early signs of the disease, so could you have misdiagnostic the healthy ones that might have like a early sign that you'd miss it because of the low resolution?
Yes, you have to trust the experts. That's why I put this picture here. I didn't have enough time to comment all this, but we collaborated a lot with expert ophthalmologists. And you have to trust these expert ophthalmologists, and we did some other study of the angles and whatever, and then they classify in 4 categories. But of course, there were 2 people looking at the images. Still, they not always agree, so it's very difficult.
In a situation that you don't trust the ophthalmologist, would you have like, how would you have like a measure of reliability? Like, okay, these 2 people, it's classified in health, but might not be, like they are in the edge. Do you have anything for that?
I mean, there's no solution to this. It's the same as you have different methods give you different information. You're lost here. I mean, you're on your own. Just, yeah.
Okay. Well, I don't see any other question for a question. So, well, thank you very much, Cristina. It's been a set of very interesting lectures. Okay. Now we have a coffee break, and yeah. So,